Hello, this is a very simple demonstration of simulated annealing and a greedy algorithm for a square array placement problem. And so what you see here is I've built a little square array in Netlogo, which is an agent-based modeling language and a set of utilities. And in this particular case, it's just a regular array of nodes, and they're connected with nearest neighbors. And what I'll do now is I will randomize the graph, and now it looks like something that the dog ate for breakfast. And what we'll do from this point on, we'll just apply a greedy algorithm, and all it'll do is it'll pick 2 points and swap them, and if the overall cost goes down, the wire length cost goes down, it'll accept that solution. If not, it'll move on to another pair and try again. And it'll do that about for 600,000 ticks, which takes about 5 minutes. So I'll just start it here, and what you can see is the cost going down, and I'll pause the recording right now because it takes a fair bit of time and not much really happens, but you can sort of see it's getting a little bit more organized, and I'll come back when it's a little further along. Okay, we're back again, and as you can see, the greedy algorithm has worked its way into something that looks a fair bit more organized than it started out. And as I said, it is a greedy algorithm, so it only accepts solutions which are going to make the overall wire length lower. This is equivalent to sort of running the simulated annealing type algorithm with a temperature of 0, and that's sort of demonstrated down below here. So it's basically the final grid length turned out to be 2982 and change, and what I'll do now is I will re-randomize it, and it'll basically get back to a very random starting location, again looking like the dog's breakfast. And this will run the standard simulated annealing type algorithm. In this particular case, we'll again pick pairs, and if the cost goes down, we accept the solution as the next state, and if the cost goes up, we probabilistically accept it. So we'll just start running the simulated annealing algorithm. So a little bit different than the greedy algorithm. You see there's a little variation in the solutions that are being generated, because sometimes it accepts a worse solution, particularly at higher temperatures. And here's my temperature schedule. Not very complicated, it just decreases it by a factor at each iteration, and at every temperature it sort of runs a certain number of times. Set it up so that the greedy algorithm runs roughly the same amount of time as the simulated annealing algorithm. And what I'll do now is I'll pause for a bit and come back when it gets more interesting. Okay, we'll pop back in on the simulated annealing. You can see it's doing a little bit better job in trying to organize the nodes on this regular square array. And here's our cost function, for example, and you can see it's doing slightly better than the greedy algorithm did, with approximately about the same amount of time. This is the temperature profile, as I pointed out before. It's just going down by a constant factor at each iteration. Interesting things to note perhaps are, in places it's a bit more orderly, but there's still a fair number of connections which are long lines, which represent kind of long lines, would add a fair bit to the cost. It's interesting to note also that the simulated annealing for square array placement, at least of vanilla flavor, isn't doing much better than the greedy algorithm. One of the reasons for that is that this type of problem is considered an Ising spin glass, or equivalent to one, and that basically means there are many solutions at about the same cost, and it's fairly difficult to find an overall global minima, but it's relatively easy to find an acceptable solution. So we'll just let the simulated annealing finish out. It'll just be a couple more seconds, and it's come to a final length of 2372. The greedy algorithm was 2982. So it's an improvement, but perhaps not as significant improvement as it could be. The next thing I want to demonstrate is this thing which I call smart anneal. So we'll re-randomize everything, again making it look like the dog's breakfast. And smart anneal is just where the candidate nodes that are swapped are going to be selected from a node which acts as a proxy. It identifies a node in its neighborhood and identifies a node that it's connected to, and it tries to swap those two. Other than that, the algorithm is identical. So I'll just start it running, and hopefully we'll start seeing some improvement to the cost. One thing to note is it even though after randomization it had a fairly high cost, within a very short period of time it did drop down and behaves a little bit different, or significantly different, than simulated annealing did, and we'll just sort of wait and see where it ends up. So I'll pause for now and be back shortly. Okay, we're back again for the finishing off of the smart annealing phase, and basically you can see it's done a little bit better than this vanilla simulated annealing, and it's also getting to a point where there's diminishing return with very low temperature and plateauing out. But we'll take a look at the final solution in a second or two, and as you can see, the square array does look much better placed than it had in the previous two examples. And that's with a a very simple heuristic, which I'll hopefully be able to demonstrate when this finishes. So we'll just let it wind down, and I'll just point out a couple other things here. The heuristic was also applied with the greedy algorithm, and it didn't really make much difference. And I also have a little chill button here, which basically at the end of a run just allows you to shake nearest neighbor nodes a bit, and if it's preferential for them to swap, then it would swap. Other than that, a pretty standard simulated annealing type of example. And this is a very nice example, of course, to use because you actually know what the optimal solution is, and in this particular case the optimal solution is 1102, and as we saw with the greedy algorithm, we got down to about 2900, and with the simulated annealing algorithm around 2300, and we seem to be plateauing out with the smart anneal at somewhere around probably around 1450 or so, and that should terminate fairly soon. But it's also nice to see that there are very regular patches here, which probably do correspond to the location where the nodes were on the original graph as well. Oh, I have one other button here I could maybe mention, this radius button, and it's related to the neighborhood in which you would seek a node that you would potentially swap with one that the proxy node is connected to. So it should be winding down right around now, and as you can see, each of these took roughly the same amount of time or ticks, and that's demonstrated by these three phases here, where the greedy algorithm didn't have a temperature associated with it, the simulated annealing did, and the same temperature schedule was used for the smart annealing. So hopefully it will terminate. A bit like watching paint dry now. And maybe I'll put it on pause until it does terminate. No. Okay, so it's terminated, and the final tour length there was 1482, which is not bad considering the optimal solution is 1102. Again, the greedy algorithm didn't do very well at all. Simulated annealing, improved. It came within a factor of 2, but the smart annealing seemed to work the best. I'll try to demonstrate the smart anneal algorithm by pushing this test button. And what it has done for me, it's identified the nodes that are selected for candidate swapping. This one here isn't particularly clear. I'll try it again. And what it says is, from the pink one here, I pick one that I'm connected to. Maybe I got that wrong. Maybe it's the white one. And anyway, in any event, you're supposed to pick one that you're connected to and pick one that's in your neighborhood. So I suspect it was this one I'm close to and this one I'm connected to. And that is about it. I just wanted to see if I can drag this other window on top just to give some props to Cam Studio. That's what I used for recording this. Thanks for watching.